Okay, we are live. Good morning, good afternoon, or good evening, depending on the place of the earth where you are located now. We are starting now our first professional training on GNSS, signal processing and navigation techniques. This event is organized by Galileo Information Center, Brazil. I'm Eduardo Freitas from Mundo Geo. It's a company that is member of the consortium of Galileo Information Center, Brazil. First of all, I would like to talk about what is our agenda and how this event will work. We are going to have some presentations using PPT and also softwares and screen sharing here. The questions, you can make questions and send questions to us by chat. I see that you are already sending us some messages here in the chat. And then we are going to have some Q&A sessions by the end of the day, by the end of the presentations. I would like to thank everyone that is connected for your presence here in our event, and also the presence of Carles Mirapeix, André Almeida, Felix Antraich, and Adrià Garcia, and Jaume Subirana that are going to present here today. Before going through the agenda, I would like to invite Carles to make a brief presentation about the center, and then I will go through the agenda and then I will introduce the presenters. Carles, good morning.
Good morning, everyone. So thank you, Eduardo, and thank you all the attendees for joining this first professional training. Well, I'm the coordinator of the Galileo Information Center. First of all, I have to say that, due to COVID, some activities has been adapted to the online format. This is one of the activities that has been adapted. So we did the effort to adapt all the content, all the professionals, the professors from both universities. So thanks to them too in advance. As probably some of you has attended to some of the webinars that the center has already done. In every webinar, we do the presentation of the GIC with PowerPoint, etc. And today I would like to do it in another way. I will directly use the website in order to reinforce even the tool now that this website is getting is providing more information, because we are uploading all the activities done by the center. Okay, so I will connect my screen. Let's see if it works. Is it okay, Eduardo?
Yes, Carles, everything okay?
Okay. So, this is the Galileo Information Center. As you can imagine, the name of the center, the main objective is to disseminate the technology of GNSS technology developed by the European Commission, the GNSS, what we say, Galileo with EGNOS included. The main objective of this center, obviously, is to disseminate the usage. First of all, to increase the awareness of this technology, because we realized that during this first month of the project started 1.5 years. It's a 3 years project, but it will continue after these 3 years. So one thing that we realized is that in general, there is not a lot of awareness of the GNSS, of what's Galileo. Once we contact with experts, and probably some of you, maybe you already know it, but this is the main objective of the center at this first stage. And afterwards, obviously, to let the people use companies or other stakeholders, universities, to use this technology, right? So following a little bit the content of the website, I would say, Eduardo, can we play this video? I think it would be better if we play that from your side, that from the website. It's a video explaining very clearly.
Satellite positioning has become a vital part of our everyday lives and is key for farming, science, precise timing, and emergency response. We use it in our phones, cars, planes, trains, ships, and thousands of other applications. Initially, it was powered by an American system, GPS, or Global Positioning System. A few years later, a Russian system, GLONASS, was introduced. In 2016, Galileo, the European Global Navigation System, launched its initial services. So what is Galileo, and what makes it different from other constellations? Galileo is a European state-of-the-art system that provides highly accurate, guaranteed global positioning and super-precise timing. Once fully deployed, Galileo will consist of 24 operational satellites and 6 in-orbit spares, 23,000 kilometers above the Earth, supported by a range of terrestrial sensor stations and control centers around the world. Galileo is autonomous, but also interoperable with existing satellite navigation systems, and many devices combine 2 or 3 constellations to increase accuracy and reliability. While it can work with other systems, Galileo is unique. First of all, it's European and under civilian control. All other systems are operated by the military, so it provides Europe and European citizens with independence and sovereignty. Galileo also provides a range of new services, including search and rescue, PRS, a secure service for government applications, and a more precise positioning for commercial applications. By offering dual frequencies as standard, Galileo will in fact deliver new levels of real-time positioning accuracy and substantially improve availability of the service under the most extreme circumstances. By deploying Galileo, Europe also minimizes the risk of other navigation systems being switched off or degraded. Galileo is the result of unprecedented European cooperation and innovation to offer people across the globe a new, reliable, independent civilian navigation and timing system that will power limitless applications.
Okay, Carlos, I think you have to turn your camera.
Okay. Do I need to do something, or
just turn your camera on again? Please.
Okay. Is it charging?
Okay, Carlos, are you going to turn share your screen again?
Yes, I'm trying. It's like a kind of loading.
Let me turn it off. Just a minute. And please try to share again.
Okay.
Yes. Now it's perfect.
Okay. Thank you, Eduardo. Okay. Well, as you seen in the video, I think that without getting in depth in all the what's Galileo, the benefits, etc., I maybe will highlight 3 key aspects. One is that well, it's a civil origin platform. It's not the origin of the development is military, is managed and focused and addressed to civil benefits. But maybe the most one of the most interesting things is that the focus, the approach of this satellite is the integrity. I mean, the idea is that all the services are incremental. The Galileo, the idea of the usage of Galileo is not switching from other systems like GPS or GLONASS, etc. The idea is to include that, to develop receptors with that can include a multi-channel and multi-system, so another satellite system like Galileo, in order to improve the global signal and performance of the devices, right? And lastly, some characteristics, services like search and rescue or high accuracy services that it's going to be ready in some month, are some of the benefits of these new systems compared to the ones that has been working for since many years in the market, in the system, right? So what is the main let's say the 4 pillars that we say of the center, no? Which are the benefits, or which are the advantages that you can take from the Galileo Information Center? First one, we try to understand which are the opportunities, market opportunities that the Brazilian companies can take advantage on. No? So we have done some market reports and researches, and according to the opportunities that we see in the market, we organized different webinars in order to provide, to share this information to as many stakeholders as possible. Afterwards, obviously, we can provide a lot of information. As I say, that we see that at this moment, the awareness of the system is quite low, so we are focusing on disseminating the existence, the awareness, the benefits, the global benefits of the systems. So that's why most of the cases, even in the website, you will see that the information is quite global, right? It's not very indeed. But for those that require or that would like to have more detailed information, obviously we're organizing the webinars with experts, and for those that has concrete questions, we can get it and redirect it to the experts that we have in the consortium or to other institutions that we have direct link with them. Another part very important is the training and hands-on workshops. So this is where this professional training fits. Obviously, it's important to know that it exists. It's important to understand that there is opportunity. But if the Brazilian companies or stakeholders wants to use it, they will need professionals. So the training and this kind of activities, it's crucial, and it's very important in this project too. And finally, institutional networking obviously is one of another of the key points for this kind of projects. Just a quick view of who is behind this project. I would say that the most important thing is that we are 9 companies. 5 are from Europe and 4 are from Brazil. That means that the approach of this project is that we really want to understand what's happening in the country, and we are using a lot. We are taking as much advantage of the knowledge and expertise of the Brazilian partners like Parque Tecnológico, Mundo Geo, and the University of Cairo. As you maybe have seen before, we have the UPC University in the group of the European partners. So jointly, these 2 universities are those that are organizing this activity today, the professional training. Okay. Just I will jump this part because we have already seen it. Here we have, as we said, the frequent asked questions. just a direct link to the main important, the first questions that someone that has not any awareness about the existence of the systems of this system can have, no? Starting by what is Galileo with the video that we have already seen, or how can I know if my equipment is Galileo enabled? You click here, you have your answer, you have some links here, and can I use Galileo in other regions of the world, etc. Right? All these questions are already answered, and even we know that nowadays the user experience is quite important. So we try to gather to present most of this information in a video, in a more nice experience. So spending, I don't know, maybe 20, 30 minutes watching this video, you can have all this first layer, I would say, of information about the system, right? Contact, etc. And here it's what we have the webinars. I would say that, as I mentioned at the beginning, this project obviously was not, the origin was not on an online project, but due to COVID, we have to adapt all the activity to online. That's why many of the activities has become a webinar format, let's say, or this kind of like today, professional training online. So here in the webinar menu, you can find the different webinars that we have done. Some of them organized by GIC, and some others are the GIC participation and other events. For instance, the first one, in fact, was a kind of an introduction of the professional training that we will have today. Here you have the video and the presentations that can be downloaded, okay, with some information of each event. And this we try to have it for all the presentation. The last one was a webinar for precision agriculture. Again, you have here the video of the whole webinar, the presentations, the PDF presentations, and I invite you to check it, because, as I said, these webinars are we say a kind of a follow-up of the market research insights, right? I mean, when we see that there is opportunity in precision agriculture, it's when we decide, okay, we can organize a webinar, bringing experts. In this webinar in concrete, it was great because we had people from Embrapa, people from Brazilian companies or institutions like Embrapa, San Martinho, Trimble. So people from Brazil that have a real experience on the topic, precision agriculture, and in that case, on the benefits of Galileo, because they are using Galileo in their receptors, okay? And I will add that in all these webinars, there are a lot of students and professor university profiles attending. So I think that it can be very interesting for you to check all this content in order to take advantage of the following activities of the center. That's more or less what we have done till now. And I would say that this will be the activity that is running today. So now I will I will explain a little bit what activities that are coming in the future, in the short future. So starting by the professional training today, here you have the link with the registration link and the program. At the end of this page, you have here a button with a download professional training material. I invite you to click on this button and to download the material. Is a WeTransfer link. So we will share this link through the chat in the platform that we are using now. But you can go now and download this material. Okay. I would say that another activity that it's promoting is the, let's say, a double PhD that is, it's going to be, let's say, offered or provided jointly with with the two universities, the University Federal do Cairá and University Politécnica de Catalunya. So if any of you are interested on developing or doing a thesis or master on this topic in a global navigation satellite system, you can have a look to this link. I will provide this link to the chat in a moment. Here you have some key information. All the professors that are involved in this PhD are the professors that will be doing this professional training. So you can take advantage of that too, asking questions directly, maybe not in the public chat, but afterwards, or how you think it would be better. And finally, I would say that another kind of activity that we are developing, we started last week, is working groups. So it's a kind of a follow-up of the webinars. So again, if we do a market research and we see that there's can be opportunities for Brazilian companies in precision agriculture, then we do a webinar in order to spread the information and invite the local Brazilian companies. And afterwards, we created this working group. This one was last week, but we will do different coming sessions for this working group, and it will be a working group for 3 different areas. One is precision agriculture, that one has just started. Another one that will be focused on aeronautics or aereo, and the last one related to transport or fleet management. So I invite you again to follow all this information, this activity, all these activities, or when the registrations are open, Mundo Geo is communicating these activities, and obviously through our social media, you can be informed too. And I think that's all from my side. So, Eduardo, let's see if I do it well. It's okay? Okay.
Everything okay?
So if anyone has any questions about the Galileo Information Center, it will be a pleasure to answer them.
Okay, thank you, Carlos. Let me now just present the agenda and introduce all the speakers, and then we'll have a quick break just to make the final checks, and then we will start the professional training. I will share my screen. Okay, Carlos, could you just confirm, please, that you can see my screen?
Yeah, I see yours.
Okay, thank you. Just a minute. Okay, so we are going to have this first day with we have already had this welcome and presentation of the Galileo Information Center project. Afterwards, we are going to have an introduction to GNSS, the next break, and then an introduction to GLab 2 suites, and the conclusion. You're going to download this software to make the practice. The second day, we're going to have multiple sex and spread spectrum ranging, then ship pulse shapes and multiplexing, and then the conclusion. The third day, signal acquisition and parameter tracking. The fourth day, the overview of GNSS positioning techniques and analysis of GNSS models, components. And the final day of this professional training, the subject will be precise point positioning, or PPP, and kinematic orbit estimation of a LEO satellite, and then our closure. Of course, you can download the materials of the professional training in this link. I've already put this link in the chat for you. And now let me introduce the presenters. We have here Dr. André Almeida, is an associate professor in signal processing with the Department of Teleinformatics Engineering of UFC, Universidade Federal do Ceará. He has over 50 referred journal articles published and accepted, 100 conference papers, and 5 book chapters. Dr. Almeida is a senior member of IEEE and an elected member of the Sensor Array and Multi-Channel Technical Committee of the IEEE Signal Processing Society. He is a Productivity Research Fellow in the CNPq, the Brazilian National Council for Scientific and Technological Development, and his research interests include the topics of space-time array processing, multi-antenna communications, multilinear algebra, and tensors with application to signal processing. Dr. Felix Antraich is a professor with the Department of Telecommunications in the Division of Electronics Engineering at the Aeronautics Institute of Technology, ITA, or ITA, in São José dos Campos, Brazil, and a member of PGETI of UFC. Dr. Antraich is a senior member of IEEE and an elected member of the Sensor Array and Multi-Channel Technical Committee of the IEEE Signal Processing Society. He is a Productivity Research Fellow in the CNPq, and his research interests include sensor array signal processing for global navigation satellite systems and wireless communications, estimation theory, wireless sensor networks, positioning, localization, and signal design for synchronization. Dr. Adrià Rovira Garcia is a PhD lecturer at the UPC, awarded with a Marie Skłodowska-Curie Fellow from the European Union and senior research engineer at GIC. He co-authors more than 21 papers in peer-reviewed journals, 2 book chapters, and over 30 works in meeting proceedings. His current research activity is focused in enhanced algorithms related with the real-time fast precise point positioning, fast PPP technique for high accuracy GNSS navigation. And finally, last but not least, Dr. Jaume Sanz Subirana is a full professor at UPC, senior research scientist, and co-lead at GAGE. He has published over 75 papers in peer-reviewed journals and about 220 works in meeting proceedings, with 4 Best Paper Awards from the U.S. Institute of Navigation. He co-authors 5 patents on GNSS and 4 books on GNSS data processing. His current research interests are in the area of GNSS data processing algorithms, assessment of rain algorithms, GNSS ionospheric sounding and scintillation, augmentation systems, and high accuracy GNSS navigation. I think we can now give welcome to the audience, the presenters, and then we will have a 5 minutes break just to make the final checks with the cameras and the audio, and then we start the professional training. I will ask you a few words in this. Let's follow the presentation order. André, good morning. Welcome.
Good morning, everyone. Welcome.
Okay, Adrián, Felix, welcome.
Good morning. Well, welcome to this training. I'm very excited to host half of the week from our side, and I thank already Mundo Geo for organizing the professional training, and the Galileo Information Center in Brazil also for organizing it, and being part of the project is also a great honor and a great joy. And so I hope we can deliver also this joy to you this in this week. So have fun with the training.
Thank you, Felix. Hello, Adrián. Welcome.
Hello, good morning, everyone. Good afternoon, depending where you are. It's a very good, very big pleasure for us to start this training. This on GNSS. As you can see, it's a global event. We have the lecturers and attendees all over the world. So I hope you have fun and you learn a lot of things during this week.
Thank you. And finally, Dr. Jaume, welcome. Bienvenido.
Hello, everyone. I'm more than happy participating in this professional training. I hope that after this training, you will have not only the information, but also you...
I think the audio is a little low.
Okay. Hello, can you hear me?
Now it's perfect. Yes.
Much better, eh? Okay, sorry. Hello, everybody. I'm more than happy in participating in this professional training. As I said, I hope that after finishing this training, you will have not only the knowledge, the information, and the ideas that we will present, but also you will have the contact points. You will have our contact, but also you will have contact from the students participating here. And I think this will be another value. Okay, nothing more, just enjoy, and we will keep in touch during this week. Thank you.
Okay, thank you all the presenters, all the speakers here in this professional training. Also, I would also like to thank Carles for your introduction to the Galileo Information Center, Brazil. Now we are going to have a 5 minutes break just to have the final checks here with the speakers and make and turn on all the presentations on, and then we are going to start our professional training. So now it's 5 a.m. in Brasilia time. We are going to start at 9:10. Okay, so just 5 minutes and we will be back soon. Bye. Okay, let's start our professional training on GNSS, signal processing and navigation techniques. You're sending your comments and your questions in the chat. We are receiving here your questions, and by the end of the day, we're going to answer some of them. If you have any questions about the Galileo Information Center, you can also send us. We can make it clear for you. And Mario Moreno, he has a question. He wants us to share again the links. So Mario, just a minute. I will send you again the link to download to access the agenda and also to download the materials of this professional training. Let's just wait for the first presenter, the first speaker, and then we're starting. Just a minute. Okay, let me just check who is the first speaker, and then we're going to start. Just remembering that it's necessary to open again the camera and turn the screen on.
Hi, Eduardo. I will be the first speaker.
Okay, Felix. Okay, you can. We are seeing now your camera. Everything is okay. When you want, you just need to
share my
turn
screen.
on your screen. Okay.
Okay. And there it is. Ah.
Okay, Felix, we can see now your presentation. If you have any problem with the screen sharing or the audio, I will enter here with my microphone open, and I will tell you.
Okay, thank you very much. So good morning. The first talk I'm going to, or the only talk I'm going to give today, and then we will continue together tomorrow and the day after tomorrow, is on an introduction to GNSS. And my intention with this talk is to introduce some basic terms and give some basic information about GNSS. And I think these terms, they will be used in the next a couple of days a lot. So I want to make sure that you know what we're talking about. So this is the outline of the talk I'm giving today. So it's we will start with some basics. Then we'll have a look at the system architecture of a global navigation satellite system. We'll discuss some performance measures. Most of you for most of you, accuracy will pop into your head, but this is not the only one, and it's not even the important one for GNSS for many applications. Then we'll have a look at the frequency bands, because there's a lot happening in the provision of signals in the GNSS world, because all the systems are not. I mean, 4 systems are operational with a current signal plan, and they're all in a current or in a continuous mode of optimizing and evolving. So there's some. I'll give some information what we can expect from them in the next couple of years. And I also want to introduce some augmentation systems because they kind of belong to the GNSS family, but they're not global navigation satellite systems, but for example, space-based augmentation systems or ground-based augmentation systems. And we will shortly only discuss what's their purpose and why are they operated. So basic, so what are GNSS? So global navigation satellite systems. These are systems that operate worldwide, so you can receive them all over the globe. They're providing positioning, velocity, and it's also important to understand they also provide timing information. So if you want to synchronize different platforms or anything, this timing information can also be very, very helpful in many applications. And it is for example, the stock market and other applications is already timed with GPS or GNSS time. So you can synchronize different platforms that are way apart from each other, for example, and that's a great benefit. Base stations of mobile phone terrestrial systems are synchronized with this, for example, and other things. They're using satellites in orbit to transmit the signals for ranging. So you have the, let's say, the interface of the user to the system are these signals that are transmitted by these satellites. And with these signals, we have to perform ranging. And with this, we also perform, introduced to the ranging, we also do the synchronization between our device and the system time. And with this, we can synchronize our device or the device that is calculating the position also to the GPS system time. And thus, we can also synchronize different terminals that are way apart from each other to the GNSS system time. We have several operational systems. So it's the GPS system for a long time and the GLONASS, the Russian system. And the systems that are still, I mean, Galileo is already operational with initial services and also now with the high accuracy service. And so we should count them also under operational systems. I put them here still under development. It's maybe not fair, but Galileo is not fully operational as I have understood, but they're still in a development mode, but very close to full operation. There's also the Chinese system called Beidou, and they're also very close to full operation. So this separation maybe is not good anymore. There's also some regional systems. These systems, the satellites, you can only see or receive the signals from these satellites in certain regions. And there's, for example, the quasi-zenith satellite system, QZSS, which is a Japanese system. And then logically, you can only receive the signals of these satellites over Japan and an area in Asia. And then there's also the Indian regional satellite system, IRNSS, which was recently renamed to the Navigation Indian Constellation Navig. And they are also providing services over India and surrounding states. So you have a lot of, so the message here is also you have a lot of systems. You have quasi 4 operational constellations where you can already receive most of the services of them. So you have global, and for each of these systems, you can receive at any point at the globe maximum like 9 to 11 satellites. So you have a lot of satellites that you can work with. All these systems are interoperable in your device usually. So, and we will see in the frequency plan what interoperable means. They share the same frequency bands. So your device can connect to one carrier frequency and receive all the 4 satellite systems. For example, if you tune into the L1, E1, B1, or whatever the name, the different systems have different names of these carriers, but it's the GPS L1 carrier that is all that you all use in your cell phone for several years already. And so your cell phone can tune into these signals, and then it's only a receiver change. I mean, there's a hardware change also necessary, but also it's mainly a software change to work with all the systems. Your mobile phone, if you have a newer generation, is already working with all the 4 systems. And you can see this when you download several of these. There are several apps available where you can have a closer look into the GNSS data on your phone also, if you want to play with this. Yeah, the basic principle of GNSS positioning. So the user's position can be unambiguously calculated in 3 dimensions, knowing the distance. So the range to 4 radio sources at known locations if transmitter and receiver are synchronized in time. And so we have 5 equations, because this is a nonlinear system. So we have 5 equations with 4 unknowns to solve in the end. So 1 unknown per dimension of user position. So X, U, Y, U, Z, U. 1 unknown for the time difference between the system and receiver time scale, and 1 equation per range measurement. So we have, this is our range measurement, while here Xi, Yi, and Zi are the positions of the respective satellite, and then Ri is the range to this satellite, where Ru is the vector from the origin of the coordinate system to the user, and Ri is the vector pointing from the origin to the satellite in this example. And we can also, so we have a system of nonlinear equations, so that's why we have to use 5 equations here to solve for 4 unknowns. And the intersection, you can also look at this graphically. You have an intersection of 4 spheres. The spheres have a radius of the range, Ri's, and in the intersection and the origin of the spheres is around the satellites that are transmitting, and the intersection of the 4 spheres is your position. And then we can solve also for the timing difference. Typically, only 1 solution of this system is near the Earth surface. So the system of nonlinear equations has usually 2 solutions, and and one of them is close to the. So if we only use 4 satellites, for example, then we have 2 solutions, and one is only close to the Earth, and that's why we can use the Earth as a 4th sphere to intersect with the 3 satellites already received. So 4 satellites already received. So this has to be the 5th sphere. I'm sorry, and that's why we have only 4 equations then, where we can select the solution of this system of nonlinear equations that is closer to the Earth. So that's why we only need 4 radio. We can also work with 4 radio sources. With 3 radio sources. So we can work with 3 satellites, also receiving 3 satellites, and with a 4th sphere, we can get this also positioned. Yeah, the system architecture. We have 3 segments. So there's the space segment that is very obvious. This is the interface to the user segment. The user segment is everybody who is using the system. And the space segment is just the satellites, or it's all the satellites, and it provides the interface to the system. And then we have also the ground segment. The ground segment is very important because it communicates with the satellites. It determines the position of the satellites. It determines the clock offsets of the satellites. It uploads the message to the satellites. It keeps the satellites on their orbits. It keeps the satellites healthy. It makes all the maintenance checks and everything that is necessary. The ground segment is a huge endeavor in the system. Besides the space segment is also very challenging because they have a lot of challenging technology on board the satellites, and also the development of these technologies is challenging, and this is challenging for any of these systems because they have all chosen a slightly different part of implementing the technologies and different technologies. But the user segment is the ground segment is something that is not really known to the user what they are doing, and this is also a huge endeavor with a lot of effort behind this operation of these systems. What we can see here is the ground tracks of the GPS satellites from the 1st of September in 2015, with 24 operational satellites in medium Earth orbit and 7 sphere satellites. 7 spare satellites. Here the red line, the solid red line marks the satellite 28, and you can see where these satellites are located around the Earth. Mainly they're located around the equator, and then the northern and southern parts of the equator. So you have maybe the reception on the poles is a little bit degraded in the number of satellites. By the way, this is taken from the book of it's from Springer, the Handbook of Global Navigation Satellite Systems, a very nice reference if you want to learn more, especially about Galileo, GPS, the different systems. I can recommend reading this. A great part of it is also online in Google Books, freely available, but I also recommend you buying the book. It's a very complete book with many, many pages covering all the different aspects of GNSS. All the systems, they are nominal orbit, so their nominal orbit altitude is around 20,000 kilometers, which is a MEO orbit. And they have different constellations, different number of spheres. They have the satellites on, so the geometry of the satellites is slightly different. You can optimize with this the design of the constellation, the reception in different areas of the globe. And the different systems, they have done this, choosing different constellations and optimizing the reception for different areas. Here we see, for example, and I mentioned this already, the ground system, the ground segment of GPS. You already see that you need stations around the globe. They're all located closer to the equator. At least you have to search here for the blue dots and the green triangles, because they are, as you can see, they're the ground antennas and the Air Force monitoring stations. In this case, these are Air Force monitoring stations because the system is operated by the Air Force in the United States. You also have then a master control station and an alternative master control station. You can see them here with the red star and at Schriever Air Force Base in Colorado, sorry, and the alternate master control station in Vandenberg Air Force Base in California. And then you have also remote tracking stations. They're given here with the yellow triangle, and then you have also with the purple dots the NGA monitoring stations, the National Geospatial Intelligence Agency monitoring stations. All these stations, these ground stations, they're used to control the constellation. They're used to calculate the orbit, precise orbit of the satellite, at least the part that is provided by the system. I just want to mention there's a lot of ground stations, also public ground stations, and they are also used to provide this information in a much larger or much better accuracy usually than the GNSS systems itself. they provide these information. For example, the precise orbits that you need for centimeter accuracy positioning, they might be more accurate provided by a civil entity, for example, the International GNSS Service, so the IGS. They have hundreds of stations around the world, and they're calculating different, they call that products. They have, for example, precise orbits, where you have very accurate positioning of satellites. You have additional error corrections. They also provide, with their reference stations, you can also look into ionosphere corrections and so on. So there's a lot of these additional services that you can get provided by additional service providers that help you, especially then in the high-end precise point positioning, which we will see in the end of the week. These are the let's say the measures that are driving the accuracy in the end. So you have to have very exact clock corrections, very exact orbit or ephemeris data in order to get to centimeter accuracy with your receiver. But there's also provided by the message of all the GNSS systems. There is already orbits, clock corrections, and so on. There's also ionosphere correction is provided based on parameters that are fed to a model. So self-standing, you can use GPS or GNSS, all the systems self-standing, but you can also add additional information that is more precise than provided by the systems itself. And there's a lot by the internet, provided by the internet, by reference stations, and so on. So let's talk about performance measures. We already talked about accuracy already. So, but there are more than there's more than accuracy for GNSS. So accuracy is the solution error, the positioning solution error. And this is mainly the performance that most people talk about. Yeah, it's very accurate. But there's also availability. Because the accuracy is nice to have, but maybe the system is only accurate twice a day. And then you can say, hey, it's very accurate, but it's not available. So we want to have accuracy, but also available accuracy. Right, so availability is the portion of time GNSS can be used with a certain accuracy, and so availability is very important for many services because it's even sometimes more important than accuracy because maybe your service depends on a GPS solution or GNSS solution, but it is not so accurate, but available. Yeah, and this is, and you maybe have other sensors that are helping you to get to a higher accuracy and localization positioning, but you need also a solution from the satellite navigation systems to stay accurate. But the solution from the GNSS does not have to be so accurate, but you need availability. And then for safety critical applications, these are applications where lives are at stake. Unwarned large solution errors can seriously increase the risk of an accident. And this is like, for example, autonomous driving and possibly causing damage of goods, injuries to people, or even death. And so it's autonomous driving, landing aircrafts, docking ships, these kind of things, where lives of people are involved. And so it's not an application where you walk on the street with your phone, because here we rely on your eyes also, that you not just walk blindly on the street. So errors can occur without violating the accuracy and availability specifications. So we maybe still have accuracy according to the specification and availability, but there's also two more measures. One is the integrity, which means measure of the probability that such hazardous situations can take place. Or, in other words, can I trust the solution that my receiver is displaying? So can I really trust this position that the receiver is calculating, or is he calculating a position with a huge error? And I want to know this. I mean, as a pilot, when I land my aircraft, I would like to know, can I land now, or can I trust my solution, or do I have to wait, or do I have to make another turn and see if my positioning solution can get better when I reach again the approach? So this is an important information for especially safety critical applications. And then there's continuity also, and this means the availability without interruptions. That's also important, because availability is calculated maybe throughout the day. You have like 95% of the time the system is available with a certain accuracy. Yeah, but you need for certain applications like docking a ship, landing an aircraft, you need continuity, especially you need continuity during your approach with an aircraft. So you start your approach and you need continuity of availability and of accuracy for a certain time, for like 6, 8, I don't know, 10 seconds. You need continuous availability and accuracy. And on the other hand, you want to know, can I trust my position? So these are the 4 performance measures that are important. And as I mentioned, sometimes accuracy is not the most important one. But let's see what accuracy, what's the definition of accuracy. And I took here the definition of the U.S. Federal Navigation Radio Navigation Plan from 2008. So in navigation, the accuracy of an estimated or measured position of a craft, vehicle, aircraft, or vessel at a given time is the degree of conformance of the position with the true position of the craft at that time. Since accuracy is a statistical measure of performance, a statement of navigation system accuracy is meaningless unless it includes a statement of the uncertainty in position that applies. So this is the definition of accuracy, and you see already it's a statistical measure. So you like give a root mean square error or a standard deviation. So that means in 95% of the time you can expect you will be inside this measure or something like this. Then there's availability. So the availability of a navigation system is the percentage of time that the services of the system are usable by the navigator. Availability is an indication of the ability of the system to provide usable service within the specified coverage area. It is a function of both the physical characteristics of the environment and the technical capabilities of the transmitter facilities. So it is, the system itself can have errors, failures. We have seen that in the past. So the GNSS system itself can produce failures. There have been satellites transmitting the wrong message. There have been satellites with outage, with power outage, with problems with power amplifiers. Everything already has occurred. And this is terrible if this occurs during an approach with your aircraft. So you have to know about this. And the other thing is what they mention here is the environment. So, I mean, it depends greatly. The service availability depends greatly also on the environment where you are. So if you are in a city with high houses around you, or skyscrapers even around you, the reception to the satellites is limited, right? So the availability of a service is maybe justified here. The availability is not justified here, and you maybe have to see how you can enhance your availability. Maybe using not only one system, but several constellations, then you have more satellites available, and maybe then an availability of your service will be back. Yeah? So you will have it, you can achieve this availability. Okay, so you see also it's not only the system itself, it's also strongly the environment that you work in. So that's why it is a very difficult question to answer for people when people ask, okay, what's the accuracy of GPS? I mean, there's a defined, or what's the accuracy now of Galileo and how is it better? This is a discussion which is difficult to lead because it depends very strongly on the environment the user is in. So, but you can say in general, there are, if both receivers are in the same environment, then we can see this and this. For example, we have for Galileo and already all the satellites, they have dual, triple, even quadruple frequency availability. If you want to split up the E5 carrier into 2 signals, you have 4 carriers available, and they're all transmitting, and all satellites are transmitting these signals. In case of GPS, the constellation is not fully deployed, has not fully deployed yet the L5 signal, the second one of the further civilian or open frequencies, and there's also L2C, but also not provided by the full constellation. So the GPS system is still in the deployment phase of, let's say, the second civilian frequency, while the Galileo system has already, for all its satellites, available freely for everybody, 2 frequencies. At least 2 frequencies or 2 signals at 2 different frequency bands. And this is very important if we talk about accuracy to correct ionospheric errors in the non-disturbed or in the non-turbulent ionosphere. So here maybe Galileo has at the moment an advantage, but okay, GPS will catch up soon when they launch more satellites. On the other hand, yeah, this will take time, but they're continuously launching. So let's have a look at the other measures. So integrity is the measure of the trust that can be placed in the correctness of the information supplied by a navigation system. Integrity includes the ability of the system to provide timely warnings to users when the system should not be used for navigation. So this is the only thing that you can do then if you have, for example, if your integrity algorithm tells you, hey, I'm not sure if this solution is correct now, then you can only say, okay, I cannot use it right now. I mean, what else, what you want to do? You can fall back to other means of positioning at that time, and then try again if at a later time you have the needed integrity, the needed trust in the information supplied by the navigation system. And then we have also continuity. The continuity of a system is the ability of the total system, comprising all elements necessary to maintain craft position within the defined area, to perform its function without interruption during the intended operation. More specifically, a continuity is the probability that the specified system performance will be maintained for the duration of a phase of operation, presuming that the system was available at the beginning of that phase of operation. So it's already what I said. So at the beginning of our landing operation with an aircraft, we want to be sure that during the landing, we have availability until touchdown. Yeah? So that's continuity. So you have to provide continuity also. And you can see now that accuracy maybe is not the biggest demand from applications. Yeah? You maybe have continuity is maybe more important, maybe, and then you need to wait in your application. You have to see how you want to weight your, for example, your signal processing. Do I need a very expensive signal processing to achieve high accuracy? Maybe I can live with a less complex signal processing, get a less less accurate positioning solution, but I get one that is more orientated to availability and continuity. So I want to have a service available in a continuous time, and this is more important for my application. So you have to be aware of these four performance measures, and for different applications, the weighting of these measures is different. For example, for safety of life, integrity and continuity maybe is more weighted than accuracy. Okay, so let's move on to the frequency bands. The frequency bands, this is a part that shows us very clearly the interface to these systems. So this is what our device has to connect to. And we see here the frequency plan, which I have to say is constantly changing. So this is just it's a moment in time of GNSS, but it is not the carved in stone signal plan. But there is the current information is provided. We have here in the first line we have GPS with its 3 available carrier frequencies. As I already said, not all the satellites already provide the L5, which is on the left, as you can see, the green signal on the left in the first line, on the first row, and then the second carrier is the L2 carrier, where we have a military signal and we have one civil. So the civil signals are all given in green here. And we have the green and yellow. They're given also in yellow, some of them. But here the L2, which L2C, which is the second one of the not the second, but it's one of the open services of GPS, but also not deployed already on all satellites. So you have a limited availability of these signals because not all satellites transmit them yet. And then we have the famous L1 on the far right in the first row, which is the CA BPSK1. That's the satellite. That's the signal that you can receive in dark green and pointing towards you maybe. This is the signal that is received by your mobile phone, and originally was or still is a service that is just the acquisition signal for the military service. So you see the origin of GPS is in the military domain, and then the civil users started to use one of the signals that was open, partially open until 2000, and then fully open after 2000, the year 2000. And they're using a signal up to date. So your mobile phone is using a signal up to date that was not intended for this use. It was intended for a fast acquisition for the military service, but it provides until today very fast acquisition for, especially for the mass market devices. They love this signal because the receiver with low complexity can get a very fast acquisition of the signal, and then also fastly the first position calculation. And if we go down, we can see GLONASS. The second row, GLONASS took a different turn, and we will learn about this week. So all the systems except GLONASS, they have used code division multiple access, and we'll talk about multiple access tomorrow, as the multiple access for the user to access the satellites. GLONASS took a different approach. They used frequency division multiple access. And what's the difference of the two? So code division multiple access, so each satellite transmits a specific code, and if the user uses the code in correlation, he can separate satellite 1 from the others if he uses the code 1. So the code of satellite 1, and if he uses the code of satellite 2, he can only receives satellite 2, and so on. The satellites are transmitting all the time in the frequency band their signals. GLONASS took a different turn, so here each satellite has a specific signal band, and the satellites are separated by these subbands, so that's why you have here these arches. You already see there's a planned a GPS, there's a planned CDMA signal, also the L3OCD, and it was already transmitted by some satellites, but it's still in build up, and they have also plans to transmit a code division multiple access signal on the L1 frequency. You see that here also in the GLONASS modernized row that's below. They have some plans to transmit CDMA signals. Then we come to Galileo. Galileo provides with all its satellites from the beginning these 3 major bands, and you can split one of the bands, the E5 band, into 2 bands, the E5A and the E5B, and which is provided by this outboard multiplexing. We'll talk about this also during this course. What is this? How is the signal generated? How is the signal properties? How is the signal generated on the satellite a little bit? And you can see here also the on all the 3 signals, on the 3 bands, we have civil signals. You have here, that's in Galileo, this name changed. So the yellow one is still here called commercial service. Now it's called the high accuracy service, and started already provision. High accuracy service is especially interesting for precise point positioning applications, because it provides additional information to the user for these high accuracy applications. And this is one of the first satellite systems that, or it's the first that provides this information freely for the users, which is a very big advantage of Galileo, besides the capability of being multi-frequency operational from its start. But okay, that comes with the that Galileo started a new constellation, and they started as a focused civil system. So they focused on the performance of civil users. I mean, the military user also has 2 frequencies in Galileo, and don't forget about this. Talking about a frequent civil controlled system, that's correct. It's controlled by the European governments, but in the end, there's also a governmental and military service, which is the public regulated service. And you can see that here in red, and also has 2 frequencies. In GPS, if you go up again, you have also the military service on L1 and L2. And then we come to the different Beidou systems. So it's already Beidou 2 and Beidou 3. You can see here, so they are having a huge change coming up from Beidou 2 to Beidou 3. They're still in transition phase. Some of the satellites, they transmit all these signals. Some of the satellites, they only transmit the BDS2. But they're very fastly launching new satellites. So soon they will have all the satellites providing the BDS3 signals. And they have, as you can see here, the same spectrum with the outboard signal as Galileo. And you can also check in the L1 frequency, so in the 1.57542 gigahertz carrier, you see the same green spectrum as in Galileo, so 2 rows up. And then if you go another 2 rows up, you can see the same spectrum with GPS. So you can see that the civil signals, they're kind of they have a perfect interoperability. They share the same spectrum. They share the same carrier frequency. The realization of the signals is a little bit different, because you can have different signals that they create the same spectrum. So the signals are realized a little bit different. We will talk about this also during the course, but they have the same spectrum. So your receiver and the receiving parts, so the front ends, antennas, they can be designed to tune to just this frequency, and you can already receive Galileo, BDS3, and GPS. And then if you just create another front end for example, L5 for GPS, that's the same frequency as E5A in Galileo and B2A in Beidou. So you can also, with the second frequency, you can cover three systems. So the good part about this is with the same hardware, you can receive 3 systems on 2 frequencies at the same time. And with this, you can provide high accuracy, especially the ionosphere corrections in non-turbulent ionosphere times is very, very important. I mean, here in Brazil, and the course is given here in the center in Brazil, we have another phenomenon, which is ionospheric scintillations. And then the multiple frequency, let's say, provision of signals on multiple frequencies does not help so much. It helps in such way that this propagation effect, it causes fast amplitude and phase fluctuations. And these amplitude and phase fluctuations, they have a certain correlation among frequencies. So depending on the strength of this effect, you can maybe still receive one of the frequencies while the other one has a very low power. And this fluctuation of power is happening between the frequencies. But it's a very strong effect sometimes here in Brazil. This effect starts after 5 o'clock, so after sunset, 5, 6 o'clock during sunset, and lasts the whole night until sunrise, and this is only happening in the equatorial regions and the polar regions, and has to do with the magnetic field of the Earth and other effects. And this effect needs to be covered by the receiver itself. So don't get confused with the ionosphere. There's most people in GNSS, they talk about what's called the calm ionosphere. So this is when the ionosphere consists out of homogeneous, more or less homogeneous plasma. And when the sun disappears, this plasma gets unstable, and thus ions recombine with electrons, and this is because we have plasma bubbles. So the plasma is not homogeneous anymore, and this causes these scintillations. Which are a strong effect and very important for Brazil for many applications, because this cuts really in your availability. So, and your accuracy also, and then finally also in integrity and continuity. You have to solve this by processing in your receiver, applying different kinds of processing. So that's enough about frequencies. So what could we see here is like a lot of systems. So all 4 global systems are transmitting on different frequencies, because I explained already, because you want to correct ionosphere, the calm ionosphere, and you want to have maybe different frequencies available for different purposes. And they also transmit different information on these different carriers, which is also interesting, can be combined, this information and so on. And you can also see that all the systems are on some frequencies are interoperable with their open civil signals. Yeah, the propagation effects, we will talk about this, but I already mentioned some of them. The ionosphere, here we can also see the troposphere, which is a little bit lower, and in the atmosphere, the layer of the atmosphere is a little bit lower than the ionosphere. We also have, and as we have discussed this already, accuracy is dependent on environment. Availability is dependent on environment, and is also dependent on these propagation effects. So the atmosphere, it can be separated in different layers, and with satellite signals, we have to consider all these layers for propagation. For terrestrial systems, we have to take into account only the troposphere, but depending on the frequency, for example, rain can be something that can attenuate our signal dramatically if we move to higher frequencies. So moving to higher frequencies introduces a lot of attenuation when it's raining, for example. And when you design a system, you have to be aware of that to say, okay, do I want to provide a service to my users when it's heavily raining? Yes, then you have to introduce that into your link budget, which is the plan for the power supply, let's say, for your signal, yeah, because you need to provide more transmit power during rain then, in order to have the same service, or you provide as much power as possible during all the time, and even then with this you can also cover a rainy day. I don't know if in my time there was still like you had when you have a satellite dish antenna and you receive some TV signals, there was some time when you have problems receiving the signals, and maybe you can correlate this with rainy days, and this is the explanation that you get, that you have high attenuation when there's a rainy day. Today the coding of the signals got much better, so the coding is resolving most of these problems with the links. But yeah, you have to take this into account. So the troposphere, in principle, for the higher the frequency gets, this attenuation gets larger. In principle, for lower frequencies, it is not a refracting, no refraction happens in the troposphere. It's only a delay of the signal and an attenuation of the signal. In the ionosphere, we have refraction. This is given here by this divergence of the signal direct path. And we have also reflection for low frequencies. If you transmit from the Earth a frequency below, I think it's 30 megahertz or something like this, and then signals are reflected by the ionosphere. So you can even not reach the satellite with these signals. So you have to move to higher frequencies to reach the satellite. And this is also why most of the GNSS systems choose the L-band as transmitting frequency, because the L-band is high enough with respect to the troposphere, low enough with respect to the rain attenuation. So we have a low frequency, relatively low frequency, 1.5 gigahertz. So the rain attenuation of the troposphere is not that large, and also the troposphere then is not a refractive medium, or is not introducing refraction. It's only introducing a delay for our signal. And then in terms of the ionosphere, the ionospheric effect is not that severe. It's much more severe for lower frequencies. For higher frequencies, it's getting less and less severe. The quiet atmosphere, the quiet ionosphere, delay and refraction, and that's why they choose this as a compromise. These frequencies between 1.1 and 1.5 approximately gigahertz, to have a good, let's say, trade-off between ionosphere and troposphere effects. Around the receiver, we have the most severe effect for civil applications is multipath, so reflections from buildings and surroundings. And I just look at the time. Okay. So from buildings and surroundings, more and more we also get for civil applications effects like interference from other systems or from people who want to disturb reception intentionally. And then there's even people who start transmitting fake GPS signals, and then this is called spoofing. And we also see this more and more in the civil domain becoming a problem, especially for safety of life applications. So in your receiver, you see you have to take care of all these propagation effects when you want to calculate precise point positioning, multipath, ionosphere, troposphere. You also have to take care of interference and maybe also of spoofing, so falsifying, fooling your GPS or GNSS receiver. Yeah, let's shortly talk about some augmentation systems that are around, and they are mostly around for the single frequency users that are the majority still, but this is changing rapidly, and they are also useful for multi-frequency users, and I'll try to explain that. So we can start with a space-based augmentation system, SBAS. Follows the differential GNSS principle for a wide area. The GNSS principle is that you have two receivers that are receiving GNSS signals, and they're close, usually they're close in vicinity, so like a few hundred meters maybe from each other. And then you can say you have maybe a reference, one of them is a reference station where you know the position of this receiver, and the receiver is making measurements. And as you know the position of this receiver, the measurements give you an indication of the propagation error, of the tropospheric and ionospheric error that the receiver experiences. And you can just tell this error to the next neighbor. So you are a good neighbor and tell your neighbor, hey, I'm experiencing like a 5-meter error here in X, Y, and then Z at the moment. And then you can tell your neighbor, and your neighbor can just correct this error because he's in the same area, and then the troposphere and the ionosphere is pretty much the same for both of these receivers. So this is the GNSS principle. So you need to have a reference station that communicates to you its error, and then you can correct that in your receiver. This is very successful and is used in precise point positioning, and then also what's also called real-time kinematics. You will learn about this during the week also. In SBAS, we have a wider area. This means that we have a wider area where we have maybe several of these reference stations, and then they don't experience the same troposphere, but they experience the same ionosphere if you're close to one of these stations, or all these stations, or these reference stations or base stations. They can calculate a model of the ionosphere based on their measurements. They can provide this to the user, and the user can correct the ionosphere error, for example. And this is what's exactly done with these space-based augmentation systems. They're also important to provide integrity information. So, for example, all the satellites of this system are still working correctly. They have no hardware failures. The messages are correctly transmitted. There's no problem. You can calmly use this signal for your operations. And this is also provided by these systems, and that's important integrity information, as we have learned. So for space-based augmentation systems, they were first introduced for aviation. And in the United States, the WAAS system, the Wide Area Augmentation System, is also operated by the FAA, the Federal Aeronautics Association. So yeah, they provide integrity, and here are the different, all the different players that we already got to know are operating one of these systems. So we have the Wide Area Augmentation Systems in the United States, the European Geostationary Navigation Overlay Service, the EGNOS system, and this is the second system that is when people from the Galileo Information Center, when we talk about eGNSS, we mean Galileo and EGNOS. And EGNOS is this augmentation system that is operated in Europe. We will, on the next slide, we see a map where these systems are operated. I forgot to mention that you receive this information from this SBAS systems. You receive them from geostationary satellites. So they are only you can only receive that in a certain area, and this is usually the same area where the base stations are located, because only where the base stations are located you can generate the information. So it only makes sense to distribute the information inside this area. There's also usually all of these systems have an internet connection, internet service as well, so you can receive this corrections and information through internet as well. Yeah, then there's the Multifunctional Satellite Augmentation System, MSAS. That's the augmentation system for the GNSS, so the Japanese system. Then there's the GPS-aided Geo-Augmented Navigation System, GAGAN. That's the Indian version of the SBAS. And then we have also the Russian version, so the System for Differential Corrections and Monitoring, SDCM. And here we can see the operation areas, or where it makes sense to receive these signals. So we have the WAAS system in North America, the EGNOS system over Europe, SDCM over Russia, MSAS and QZSS SIFE. I think QZSS SIFE does not exist anymore, and I'm not sure the Japanese had plans for some times to merge MSAS with QZSS. Maybe this already happened, and then also the MSAS system does not exist anymore and was merged into the QZSS system. Then there is also the Gagan system over India. And these systems help dramatically increasing the accuracy in these areas, especially the ionosphere correction and the integrity information that they can provide. As I mentioned already, this is very important for the single frequency users that only use one frequency, but also important for the multi-frequency users because of this integrity information, and also as maybe we will learn during this week also that the ionosphere correction with 2 frequencies is only up to a certain accuracy possible in the receiver. If you want higher accuracy, you have to switch to 3 frequencies or more, or you have to combine your measurements with additional information from these SBUS systems. Yeah, this is how the EGNOS system in particular works. So we have 3 geostationary satellites in the upper right corner that are transmitting the signal to the users. Then we have in red all over the European area, and also in North America one, in South America one station, and in the Northern African region stations. These are the reference stations or base stations. They're called here ranging and integrity monitoring stations, RIMS. They are generating the measurements, and then there is a control center in Fujino and in Torino, I think. No, this is in Spain. It's in Spain. In Spain and Italy, and they are calculating the messages and the models and the integrity information of these stations, and then 6 uplink stations. They are providing this to the geostationary satellites and back to the users. So this is how the system works. So these red dots are GNSS receivers on ground. They are measuring the signal at known locations, and based on these measurements, we can provide an ionosphere model of Europe, and with ionosphere corrections that are more precise than the ionosphere corrections based on the GNSS signal and the model itself. And we can also provide, especially for single users, a solution to correct the ionosphere. There's also ground-based application systems, and this follows again the GNSS principle for local area, and this is like the classical GNSS. The term GBAS comes from the aeronautics, so the civil aviation area for safety critical applications. This is a future, or already at some airports real, already operational landing aid for a precise landing, especially in all weather conditions. And this basically works exactly, or it works like the GNSS principle, as I explained before. We have a reference station at the airport, and this transmits its corrections to the approaching aircraft. And then the aircraft can land with high accuracy already today. GBAS is also moving on to multi-constellation at the moment, or is already there, and to multi-frequency also. But then still we can see that these ground stations are necessary because of the integrity information and so on. So, and this is the architecture of the system. You can see here the base station at the airport, receiving the satellite signals, receiving the same signals at the same time as the aircraft that is approaching the airport. And we have a VHF link, so a very high frequency link between the station and the aircraft, and to provide the information. So I'm at the end of my short introduction overview on GNSS, its frequencies, interoperability, performance measures, and the augmentation systems. If you have questions, please leave them in the chat or contact me by email. We will continue tomorrow with the lectures more on the signal processing part tomorrow and the day after tomorrow before you will enter the positioning part, which is covered by my colleagues from the UPC in Barcelona. So thank you for your attention and have a good following day with interesting presentations. Thank you very much.
Okay, thank you very much, Felix. Now we have a 15-minute break. The questions, we're going to make the questions by the end of all the presentations. And now it's 10:15 in Brazilian time. We will be back at 10:30, okay?
Thanks.
Thank you. Hello, Adria, can you hear me? I cannot hear you. No, we cannot hear you. I will turn your microphone off and then you turn it on again, please. Adria, we can't hear you. I have a suggestion that you disconnect and connect again, and then probably the microphone will be okay. Okay, thank you. Just 1 or 2 minutes, and then Adria is going to connect again.
Hello, Eduardo. Can you hear me now?
Now we can hear you. It's perfect.
Yes? Okay. Sorry.
No problem.
Okay, so welcome to the, again, back from the breakfast. Is in Brazil time. Now I will share my screen. So we are in the first day, and then we have as a last lecture for today the introduction to the GLAB tool suite. That it is the tool that we have prepared for the training. And then we will introduce it, and we will see how do we install, and so on. And then after, it will take us about an hour or so, and then we will have the last minutes of the session. We can devote to questions of this session or from the previous one of Felix. So this is the tutorial. Let me. Okay, so as you can see, this is the tutorial. It's different from the lectures. The lectures will be more theoretical, as the one that we have just had from Felix. But we thought that it was a very nice idea also to practice, to get some training by examining real data, by processing results, by analyzing and all of the elements that Felix was talking about: propagation elements, different navigation modes, and so on. So it's good to have the combination of these two trainings. So now we will introduce the tool that we will be using. Well, this is the overview of the lecture. We will have some words about the processing tool that we will be using. Then we will show some of the examples that they are actual examples from the later days in the training. So the idea is that I show you how the tool looks like once that it's installed, and you now or in the coming days make the exercise to download the material. Well, the material is in the same WeTransfer link that we have provided to you, and when you download it, you will see. Let me. When you download and open the zip and the zip folder, you will see that there are two folders, one with the slides of every day. We are in day 1, today is Monday. And also you have the software folder with the everything ready to be installed. And then because we have different users, we have Linux users, we have Macintosh users and Windows users, you have to choose which operating system you will be developing the training and install the associated files. But this we will come later, don't worry. So we will be looking at different processing modes, specifically from all of the modes that Felix was introducing, that S-bus, G-bus, and so on. We will just show examples of two modes, the standard point positioning and the precise point positioning. That's in GNSS. We love acronyms. You will see during the course today that we will use and introduce many of the acronyms. We call them for short SPP for the standard and PPP for precise point positioning. So by Friday, you will have received a lot of training about the SPP and PPP. As I mentioned, we will be using a tool, and the tool, it's called GLAB. That again, it's an acronym that is for GNSS Laboratory Tool Suite, and then we make it for short like GLAB. We will now see what is the reason to introduce this tool. We will see a little bit what are the main users and so on. And like this the fourth bullet says, everything is ready to be used. All of the tools that we will be using during the professional training, the files. Later, I will show you where to go to get more data. And I will, in particular, I will show the international GNSS service that Felix was mentioning before. Felix mentioned that there are hundreds of stations. I will show a map with all of the stations that you can choose data. So we have everything ready in this virtual USB stick. Because of the COVID, we are not doing this physical. Otherwise, we will be giving to every attendee a USB with everything ready, but you can download it from the WeTransfer link because you are many people, and it was easy to distribute everything through WeTransfer. Okay, so let's present the GLAB and the GLAB tool suite. Well, what is GLAB? GLAB is an interactive. You will see that we will get feedback from the tool. It's and this is why we call it that is an interactive tool. It has warnings, it has errors. If we misconfigure the tool, it will give us, it will tell us what is going on. What can we do with the tool? Well, it's multi-purpose. We can do many different things, and the more users we have, the more different uses that they find for the tool. It's both educational and professional. And today we are at a training. We are at a professional training. And some of you are newcomers to the GNSS, but some of you have been working for many, many years in GNSS, and you have a deep knowledge of the systems, and probably you have already your tools. But we have always these two types of users, the newcomers and professionals, very experienced people. The tool has been developed by UPC under different contracts of ESA and the European Space Agency. And these started, the development of GLab started a long time ago in 2009, and we have been adding and adding several features to the tool. Just to mention the first contracts here, but we are also now expanding the tool to handle multi-constellation and multi-frequency data. As Felix mentioned, the GNSS, all of the constellations, they are evolving. We are having more frequencies, more signals, more systems, more satellites, and we are upgrading the tool. Okay, what are the features? What are the main features? Well, as you will see in few minutes, and also the training will end with the PPP lecture, the precise point positioning lecture. The capability is to have high accuracy positioning. And this means that using the actual data and actual orbits, Felix mentioned that we have precise orbits from external providers, like, for example, IGS. We can really position very, very accurately. As we have just heard, accuracy is one of the main metrics in the GNSS analysis. So we will do high accuracy. We will get errors down to the 10 centimeters or even down to the few centimeters. These, I guess, and now we are in the first day, especially after breakfast, I guess this is appealing for some of you. How do we position with an accuracy of few centimeters using satellites that are orbiting at 20,000 kilometers? What are the different signals? What are the different techniques and methods that we need to do this positioning? Well, we will learn everything during the training. By the end, you will know how do we obtain this positioning. The second feature is that it's fully configurable. As we will see in a minute, we will have, well, you will have absolute control of the processing of how this positioning is done. And we will have some help, and this is why we say that it's easy to use. We will have some templates, some options that are very general and that will suit a lot of your users. But starting from the templates, we will be able to modify all parts of the processing. I don't know, for instance, if we want to have data every 5 minutes, every 300 seconds, well, this we think that makes sense for example, for precise point positioning. But maybe when we are processing SBAS, when we want to have a higher availability and we want to position with integrity, maybe we want the solution every second. So 1 Earth's positioning. So we will be able to change everything. The output rate, the orbits, everything. You will have control of every of the parts, of every part of the GLab. And last, but not least, is that you will have access to every step of the processing. And we will see that the GLab and then the GLab tool basically writes every step into a text file. So if by any reason you are maybe programming your code and you want to validate one-to-one with the GLab, you will see that it's very easy to check because we have full access to all of the intermediate results. So what is being read, how it's being modeled, what is the output of the Kalman filter. In every of these parts, there is some printing. And then if we activate the printing, we will be able to compare with your programs, with your codes, depending on your needs. Well, as I said, who is using GLab? Well, I assume that today we are here. Everyone is new to the GNSS. We assume that no one has never heard about GNSS, that you have never processed a GNSS file. Then, thinking in you, you will see we will be using the graphical user interface that we will see in a minute, and then you will find, we hope that you find useful, that we have a lot of explanations in the form of contextual help. We will have these templates that guide your processing, etc. So this was the first group of users that we had in mind when we were developing the GLab. But everything that you can do by the GUI, by the graphical user interface, can be executed for a second group of users that are the professionals and experts. Hopefully, by the end of the week, everyone will be an expert on GNSS, and then the GUI will not be enough for you, so you will be willing to launch multiple days, multiple process, different clocks, different orbits, and so on. So for this second group of users, more mature or more used to work with the tool, you will also notice that it's very powerful. We have the capability to run it in command line, so basically with no user interface. Don't worry, I will also show how do we run it. And then here it is very, very ready to be written inside your scripts, inside your processing, let's say your to do batch computations, to do lots of these processes. And you will see, that the transition from using the GI for the newcomers to the more experts is very progressive. Also, by working with the tutorials, you will see that at some point, naturally, you will evolve to this command line mode in which we will launch a lot of processing with the GLab. Okay, so let's see for these newcomers or students or someone that is new to the GNSS, how does it look? We have, well, at least the intention was to build an intuitive GI. You will see once that you have installed it, and then the last part of the installer, no matter if you are in Linux, in Macintosh, or in Windows, is that it will launch the graphical user interface. So you will see that it is very modular. We thought, okay, we are processing data, and we are doing the processing step by step. So let's design the interface, the graphical user interface, mimicking more or less with the same flow that the code has. And then you will see that we have different tabs. And then from left to right, and you see that everything starts with the input tab. So here we will be able to configure what are the input files if we are processing with orbits, with precise orbits, with broadcast files, and so on. Then the second tab is the pre-process. So, okay, before let's say computing the solution, there are some choices that you, the user, can make. Like, for example, the satellite selection. Here you can see the panel in which you can unselect or deselect some satellites. If for whatever reason we know that there is one satellite that is not healthy, or we want to make a trial that what happens with our positioning if we have one satellite less, we can simply disable. This is something of your choice. By default, all of the satellites will be enabled, but the user has the freedom to do this kind of choices with the tool. Then the third tab is the modeling. Here we can see all of the modeling options. You can see in all of these ticks with all of the different terms, that will be applied to the signals. As Felix said, the signals are traveling from the satellite to the receiver. And then we have all types of phenomena affecting this signal. Just to mention one that is very interesting in Brazil, that is the scintillation. The scintillation is one effect of at the ionosphere, at the upper layer of the atmosphere. So here in the model, we will have different options to take into account the ionosphere. or the troposphere, or some delays, and so on. Don't worry. On Thursday, we will be doing the we will be analyzing what is the impact of taking into consideration or not all of these terms. So what happens when our user solution, when we disable the ionospheric model or the tropospheric model, and then we will see the impact. And we will see how, in general, the position degrades when we not take into account these models. In general, as a general rule of thumb, the better we are modeling the signal, the better the accuracy will be, and the more accurate our positioning will be. This is the general idea. If from the full model we are not taking into account some parts, mostly it will be degraded, our solution. But we will see. Sometimes maybe it's better not to apply a model than to apply it. There are different questions that we will see during the training. Errors, as I mentioned, there are warnings, errors, and guidelines, the templates, and just for you to not to make a mistake. For example, a silly mistake. Imagine that we are processing data of today, but the orbits are from yesterday. And so there is a mismatch between the time of our data, what we call the observations, and the orbits. So the GLab will check for us and will give us an error. And that will tell us, careful, then there is no, the dates are different. Or as you can see, for example, if we forget to put one of the files that are needed for the processing, and don't worry, there is no exam at the end, so no, we will not track the record of all of these errors that the GLab will found during the tutorials. So this is more like to play and to understand. The final aim is that you understand what the tool is doing. We don't want to have a black box that is plotting a very nice result, but our true aim is that you understand what you are doing. Okay, so we have seen what GLab has to offer for newcomers. Let's see for more experienced users, for these professionals, for these experts. Well, it's the same idea. We want a tool that is fast and easy to configure. This does not change, no matter if we are using the GUI or if we are using the command line. And these are the typical command lines, the typical terminals. We call them terminals that we use to input commands to the tool. So we will see and all of these black windows in which we type strange commands, and then we will have the results. But it is fully equivalent. It is fully equivalent. The processing that we will be doing by the GUI, let's say by pressing buttons, it is fully equivalent to the processing that we can do by the command line. And then you will see that, okay, now that I know what I'm doing, I no longer need to open the GUI, as you will see. And you will see that the tool is very fast. This is because the core, what is in charge of performing the computations, this is written in C. And you know that all of these compiled languages, they are extremely fast when we are processing mathematical operations and we are performing this number crunching. Okay, as we said, this was a requirement from ESA, from the European Space Agency, was to have a tool as available as possible. And so that the tool was capable to work with all of these three distributions, with the Windows, with Linux, and Macintosh. And so you can try the distribution that you want, you can install it, and then the one that you feel more comfortable. At the university, we can use Linux. This is no problem, but we know that a lot of people likes the Windows, and it's convenient to do presentations like the one we are doing today. But you will see that there are no difference between one distribution and the other. Well, regarding the source code, we are using a very open license. We are using an Apache 2.0 license for the core and some other very open license for the GUI. This means that it's open source. You can take a look to the code, you can modify it if you want, and you can do whatever what you want with this code. And you can even build applications on top of our GLab. So these are very open licenses. What else? What we are having here? Well, we will have, of course, some data files to show the capabilities and to show the ideas that we will see in the theory lectures. Of course, we have the user manual, the software user manual, and we also have some files that are to describe the formats that we are using. And this we will show some examples for you that you still have 2 days before actually using the tool to get familiar with the formats that we are using in the laboratories. Well, you have access to these slides, so I will not go into the detail about what everything that can be done by GLab. We will see. Let's see the top of the iceberg, but you have the manual and you have a lot of more information in the software user manual and in our website, in the website of the UPC and the Universitat Politécnica de Catalunya, here in Barcelona, in Spain. And then if you click here, you will go to our website, and here you will see a lot of more material. I will show, if I have time, I will show a little bit. Okay, more material, and then the GLab, it's joined, or it's part of a wider package that we call this learning material package. This is the couple of books that were written by Jaume and Miguel, and they are available. The PDFs are available for free in the ESA website, but also in our website. You can download them from there. The volume 1 is for the theory, and the volume 2 is for these laboratories that are based on GLab. So you can see, of course, we don't have time to go through all of the book. The books are very thick, but we will have some ideas, and then for those that are motivated, or those that you need it, you can go on, because this is a self-learning course. Everything is ready, that one can do it at home, step by step. Everything is very guided, so that everyone can complete it. Okay, so now let's see what can we do with GLab. There are 3 examples that I will illustrate now very quickly for the standard point positioning, what we call SPP, and then the precise point positioning, what we call PPP. There are 2 different ways to process the data, and then you will see the accuracy. And then one of the key questions that the key ideas Felix introduced, how do we measure the accuracy? Here, we are lucky. We are lucky because we know where is the receiver. We will be using, during the course and today, we will be using data that is public available, and data that is that you can find on the internet, and this data belongs to permanent receivers. What does it mean, permanent receivers? Well, these are receivers that are inside permanent stations that do not move, let's say, that they are in the middle of the field or in the mountain or wherever they are, and then we know we have these receivers sitting there for many years, and we know their position very precisely. But towards the end of the training, especially the last day, we will be doing PPP and SPP. We will be doing the modes that we will be learning, also to moving receivers, and what you can think of a moving receiver. We will be working with a receiver that is inside of a low Earth orbit satellite. So a satellite that completes a revolution to the Earth in 90 minutes. And so this is a very rapidly moving receiver. And then you will see that everything that you have learned during the week will be fully applicable to this moving receiver. But this will leave it for the last day. And now let's concentrate on fixed receivers that they are static. There is one note, maybe you have already noticed, that the training is divided in 2. And the first 2 days, so the day of tomorrow and past tomorrow, they are more devoted to the signals, to all of the techniques that are involved into the tracking and to the modulation of the signal itself, the signal that is transmitted by the satellites. Let's say if we have a receiver, there are two parts. The first part, that is the one that is mainly covered, that will be covered by Felix during the first 2 days, that is more, let's say, the telecommunication part. You will see a lot of how the signals are tracked, all of these replicas, how do we generate the measurements, and so on. This is, let's say, the first part of the training. In the second part, we will see this other part of the GNSS, that is, okay, starting from the measurements. So once that the receiver has acquired the signal and has built the measurement, how do we obtain the coordinates? How do we compute our position? And you will see that these are two different and complementary parts. Our part, the part that covers, that will be covered by us, by Jaume, and myself, will be more focused to this second part. And so basically we will be talking how to process the navigation data, all of the corrections that we need to apply to the measurements, and how to estimate the position. Some of you, maybe you are also interested in how to show these results to someone else. All of these nice interfaces, more like thinking into how to display the position in the map, and so on. Sorry. So there are different parts of the GNSS chain. But just to center ideas, we will be working in this part of the after the measurements are collected. Okay, these measurements are they are stored using some standards, and again, we love acronyms. You can see the RINEX, the ANTEX, the SINEX. All of these standards are very well defined, so that if we are storing observations, we store it with given standards. If we store orbits and clocks, we use a different standard. For the station coordinates, everything will be stored with a proper standard. In order to learn, or at least to have some knowledge, we provide together with the software, we provide these HTML files that have the explanation of the formats. Maybe it's better if I show you here when you open the folder in which everything will be installed. We have the slides, the slides that we are presenting here. We have the work files that we will be using later, but we have this HTML folder that you can open it with any web browser. For example, if I open this this HTML file, you can see that we have different explained formats. For example, the observations. We have this standard, and then in every field we have the observation of the L2 observable. Now this is not saying anything to us, no? Or the L1 or the P2 C1, the civilian code at the first frequency. But we hope that you find it useful if you need at some point to understand what are these formats. And you have many of these formats that are in use during the training. Okay, this is regarding the HTML files. So now, and before I run out of time, let's just show how the GLab looks like and how you will be doing the laboratories, the exercises in the lab. When these trainings are on the same room, then Jaume and myself, we give you time, and then we go through your screens, and then we see how is the progress. Today, well, this week we cannot do this, but we have a very guided slides. You can see that you have everything on the slide, and you have even you have them how to press which is the order of the different buttons. Like for example, in this example, that is 1, 2, and 3. And then if you follow these guidelines, we will arrive to the results, and then we will raise some questions that what is going on the training. So let's do it. I minimize a little bit the slides. So basically, let me minimize everything. So basically, when you install the package, you will arrive to this configuration. We will have the GLab tool with all of the tooltips that we have seen. For example, here we have an explanation of what is this field. For example, to input the navigation file, or this other field for the observation file. You see that you have this, what we call the tooltips with information. So, for example, let's open, for example, this. This is a station that I will show you in a minute. This is a station in Brazil, and then we use the associated orbits. So this will be the basic configuration, and we are doing the standard point positioning. So we are doing very basic processing, the one that all of your smartphones are capable, and all of the car navigators, and it's let's say the basic processing. So once that we have uploaded the files, we just need to run the GLab. We see that we have a progress bar, And then we have generated some results. We can open it with any tool that you want for opening a text file, and then we can see different information. Don't worry that we will go through all of this information during the training. Okay, so we are done. We have processed the this file. This file is an station. I will show you in a minute where it's located. And if we change to analysis, this hopefully is the next slide. If we change to the analysis, we have different instructions. We have different instructions on how to plot the results. You see this is what we call the templates, and then that configure the interface for you. So if you are happy with the information that all of these templates configure for you, then we only need to plot. And after a few seconds, we will have the plot for this station. And that we have launched this plot with the Northeast tab, again, another acronym, NEU, positioning error. And then you can see that we have a time series of the north error in blue, the east error in green, and the red error in red. Okay, we said that we were taking benefit, that we are using a permanent station. The permanent station is indicated in the file name, GIC-BR. This, if we go to the IGS website, the IGS website is the website of the international GNSS service that was mentioned before by Felix. Well, here in the network, we can have a look. To all of the hundreds of stations that are participating in the IGS network. And I encourage you to find what is the near IGS station that is close to your home. Maybe you are sitting, maybe you don't know, but in your city there is a station. Here you have the details. Of the coordinates, what is the receiver that they have, and so on. If we look for this station, and this station, it's the GIC-BR. It's a station that is located in Brazil. This is the station that we have processed in GLab. As we said, we will be processing real data. We will be processing, actual data. You can see what is some photos of the receiver. We can, let's see if this opens. We can see the receiver. We can see the surroundings of this station. We can see even the antenna. At some point, we can see the antenna that is here in Cachoeira Paulista, and this is why the name comes from GIC-BR. And so we are processing, we are computing the coordinates of this station. This is the antenna that is sitting in this part of Brazil, and then during the training, we will see what is going on with this station. So this is everything I wanted to say. Well, there are other examples in the tutorial of today, and as a homework for you, as a first homework, you have to install the software. For Linux, Windows, or Macintosh users, select the software that you will be doing the exercises, install it, and have it ready for Thursday. You are here. You have the instructions. You are many. When we are in the class, we can go, let's say, one by one, seeing if you have any difficulty. Here, it is not possible. So install it before the class on Thursday. If you have any problem, something is not working well, or you cannot do this first exercise, send us an email to glab.gage@upc.edu. Because once that we install the session, we don't have time to go solving the installation problems. And that's it. Well, here we have the instructions for Windows, but there is no necessary, because you have already the PDF. And this is how we will be working, at least in the tutorials. We will have the slides, we will have the results, and we will have the GUI, and then we will be looking at all of the details, all of the characteristics of the processing. Thanks. That is everything that I wanted to say. We are ahead 2 minutes of the schedule. If you have time, and you want more information and more material, you can always enter in our website, and that you have on the bottom of the slides. And here you can see all of the material that we have available for you. So thank you very much. Now let me close all of this, and we can have some time for questions.
Okay, thank you, Adrián, for your presentation. Also, Felix. There is a question from Carlos Rocha. Could you indicate any books about Galileo and GNSS? I think you have already presented during your presentation, but do you have any further books or web links to indicate?
Yes, if you go to our website, let me again. If you go to our website, gauge.upc.edu, if you go here to the GNSS data processing book on the right-hand side, you will see the 2 PDFs I was mentioning, and this includes GPS. And let me open it. It will take a while. You can see this is for free. You can see that these are for GPS, Galileo, GLONASS, and Beidou. So here it's let's say the book, the material that we give to our PhD students when they join the group. Also, Felix mentioned the book from Tunisian. Maybe you want to give the reference, Felix?
Yeah. I think it's an excellent reference with respect to Galileo, because the information about Galileo is written by the European Space Agency in this book, and there's a lot of experts around the world contributing to the book. It's the Springer Handbook of Global Navigation Satellite Systems. The book is not cheap, but part of it is also available on Google Books. If you're interested in part of it to see if it suits to you, it's a very complete book. So you have everything from signals, models, up to geodetic applications, reflectometry, everything about GNSS. It's I think a very nice compendium, especially useful. Yeah, thank you. This is it. You can also download different chapters if you're not interested in everything, and you can buy different chapters, and they're not so expensive. And the euro just dropped a little bit versus the Brazilian real again, so it's not so expensive anymore than the beginning of during last year. But yeah, some of the book is available on Google Books also. So if you want to have a look on some chapters, I mean, there's always some pages missing, but to get information is good. I mean, there's a lot of books on GPS. Traditionally, the older ones from the 80s and 90s, they're focusing more on GPS. The newer books, they focus more on Galileo. And the one that I indicate here is the one, okay, one of my former colleagues from the German Aerospace Center, Oliver Montenburg and Professor Teunissen from Australia, University of Perth, they have edited the book. So it's more, let's say, European focused, this book, or more contributors from Europe are in there. And so I think there's more information about Galileo because the people in Europe, they work more with Galileo, and because it's their system. And so I think this is a good book if you want to get more taste about Galileo. The US, the books from US, they are very much focused on GPS usually, and they give some information about the systems from other countries, but they're not so focusing on that.
Okay, thank you, Adrià and Felix. Another question by Fabio Fagundes. He asks is there a command line option to install GLab without the administrative privileges at user space only, or at Windows, or a portable version of GLab?
No, you need administrative privileges because it needs to be installed in the C root folder, and then for this you need admin privileges. If no, maybe you can install on a virtual box. If they have a virtual box in which for sure you have administrative, in a virtual machine, so that you can install it there.
Okay, thank you, Adrià. A question from Thomas Silva. Are these formats all based on NMEA format?
No. These are the, let's say, the measurement formats. And MEA is for the output format. That is for the coordinates, basically. Is the solution. The last part that we will see on the how do we estimate the coordinates. But we were referring to all of the needed measurements, orbits, clocks to compute the solution. And MEA is only for the solution.
Okay, thank you. Lautaro Lorenzen has a question. First, he thank you for your presentation. He would like to know if it's possible to change the GNSS satellite constellation to Galileo from the GLab's GUI.
For the GI that you have now, it's only GPS. We are working on the full multi-constellation version that will be launched this summer. But for the training that we have now, it's only GPS. But it will not take long until we will do the professional trainings, the next professional trainings and the summer school of the project. We hope that we can do it with the full multi-constellation version.
Okay, a question from Carla Correa. She say, does not have this HTML folder in the document. I don't know what is this. What is this about? Maybe okay. Carla, if you can complement.
Yes, if you don't, I don't know which distribution it is using, Carla, but in any case, these HTML files are also on our website. Yes, so also if you want to use the website, it's the same information, and you are already using the browser.
Okay, thank you. And another question now by Cedric Glahaha. No, I don't know how to say it, but the question is, what is the gridded area of GLab, and if does it run for Africa?
Well, I don't know what is the gridded area, but it works everywhere. We are using satellite information, and this is a global system, so we can use it at any point in the Earth, no matter the continent, no matter the receiver type, and yeah, it should definitely run inside Africa.
Okay, thank you. Fabio Fagundes is complementing that the HTML folder is inside the GLab folders after installation is finished. So thank you very much, Fabio, for helping us. And well, we don't have any other questions today. So before the reminders, Adria and Felix, I would like to thank for your presentations here. And I would like to ask you your closing remarks, your final words for today.
Yeah, thank you very much for this first exciting day. I'm very happy that we have so many people that are following us, and I'm looking forward to the next 2 days where we will talk about the signal processing up to the measurement, let's say production of measurements, and then I will hand over to the colleagues from UPC, and they will continue then with the positioning algorithms. So see you tomorrow.
Yeah, my final remark is that thank you very much, Eduardo and Mundo Geo, for the nice organization of the training. We have many attendees from, I would say, all over the places, all over the world, and this could not have been done with your help. And as Felix said, next 2 days are for him to study in detail the signals, and the last 2 days will be for us positioning with these measurements. Thank you.
Thank you. We'd like to thank everyone for participating in this first day of the professional training. Thanks also to the speakers for their presence and their time to make the test sessions, prepare the presentations, and deliver the lectures and answer the questions. We remind you that the materials are already available for you to download from the events website. We also put the link in the chat, and we await everyone presents tomorrow for the second day of the training at the same time. Take care. Bye. See you tomorrow.